Okay, so hi everyone, my name is Zhiyuan Li. I just joined the TTIC last year as a tenure track assistant professor. So today I would like to talk about my work on chain of thought. This is a joint work done with Hong Liu, Danny Zhou, and Tengyu Ma. Tengyu is my postdoc host at Stanford. Um, so the title of paper is Chain of Thought Empowers Transformers to Solve Inherently Serial Problems. So as background, but I guess for this community, probably everyone knows. So we know chain of thought has been empirically proved to be able to improve transformers language models reasoning ability. And this is a concrete example. If you give transformers some demonstration and let the model to output intermediate reasoning steps before the final answer, it will drastically improve the accuracy of the final answer. And this is not only restricted to this form, you can also train or instruction tuning with examples enriched with intermediate steps that also work instead of just doing this chain flow prompting. So the question we want to answer here is, why does chain flow work? So there is a natural explanation from the statistical perspective. That is, intermediate steps provide extra information about task and efficient approaches to solve the task, and therefore a model can imitate. However, another paper also showed that you can even replacing chain of thought prompting by just let's think step by step. This is also non-ideal search chain of thought. And in this case, you don't actually provide more information in the demonstration. And this is the so-called zero-shot chain of thought. And even more intriguingly, people have also observed that even if you're replacing CFT prompting with incorrect reasoning steps, it still works. The language model will still get better accuracy than directly outputting the answer. So our observation here is that it seems that the form of CFT prompting is as important as, if not more important than, its content. But why? So the explanation we gave is from the expressiveness perspective, that some problems can only be computed by transformers of certain size constraints by first outputting a chain of thought. And in this paper, some problems refers to those inherently serial problems. And mathematically, then it means the problems that cannot be computed by some constant depth and polysize circuits. So that's the high-level takeaway of this paper. Next, I will go into detail setups, and let me know if you have any questions. You can just interrupt me. Okay, setup. So in this paper, we consider decoder-only transformers with constant size vocabulary and some maximum length and max. These are just some notations. We use p theta to denote the probability distribution computed by the forward path of the transformer with parameters theta and input x1 to xn. And in this paper, we consider a deterministic version where you just take argmax of this probabilistic distribution to be the transformer, to be the output of the transformer. And this process can be done in a recursive way. We use TFI plus 1 theta to denote the final token you will generate by repeating the previous generation process for I plus 1 times. So this is just a standard autoregressive generation. And to formalize the expressiveness benefit for transformer from the chain of thought steps, we also need to first introduce some circuit complexity concepts. And also, I guess for this audience, this is probably well known. So some notable existing results. A few previous papers have shown that constant depth transformers with log n precision and poly embedding size can be simulated by TC0 circuits. And these are the definitions of NC0, TC0, and AC0 circuits. So basically, TC0 circuits are constant depth circuits with polynomially many gates, with a special gate of like a majority gate or threshold gate, which has unbounded affines and outputs the majority of its input. So a well-known theorem characterizes these relationships between different complexity classes. The NC0 is a strict subset of AC0, and AC0 is a strict subset of TC0. And the separation between TC0 and NC1 is not clear, and the separation between NC1 and P/poly is not clear. And P/poly here refers to those poly-size circuits. Even though these separations are not clear, somehow complexity community have conjectured that there's a strict separation. And we will use those hardness assumptions as the main assumptions for this paper. So the hardness assumptions that we will use in this work is TC0 is a strict subset of NC1. And according to some leading figure in complexity theory, Ron Williams from MIT, his estimated likelihood for this separation is to be strict is actually 50%. And as in calibration, he also mentions like NP versus P is 80%. So 50% is not too low, in my opinion, given that NP versus NP is not equal to P is only 80%. And we can also use a weaker assumption for a weaker separation for transformers with and without DOT. And the weaker assumption is that TC0 is a strict subset of P/poly. So we'll get back this later. And now I want to introduce the formal complexity class we define for transformers. So basically, it's COT with 4 functions: Tn, Dn, Sn, En. They are like all about like size of transformers or number of steps of transformers. So in detail, we consider constant depth decode-only transformers and with absolute position embedding. That's like GP2 like architectures. And we use Dn to denote the embedding size, Sn to denote the Sn and En to denote the precision of the transformer, and Tn to denote the chain of thought, steps in chain of thought. And in particular, Sn denotes for the bits of significant, and En denotes the bits of exponents in the floating point number system. So I will explain this in detail in next slide. And in particular, if you set, sorry, this should be Tn, this is a typo. If you set Tn to be 0, then this class becomes the problems can be solved by transformers without DOT. And in this talk, we will focus on constant precision case. Basically, we assume both En and Sn are constant. And we want to use a simplified notation, which only has 2 arguments, Tn and Dn, when the precision is constant. And we have some more discussion on log precision in the paper, but for simplicity, I will not talk about them in this talk. So any question about notations? Okay. So in this slide, I will talk about finite precision modeling. Just some recap for the floating point numbers, which is the IEEE 754. So for example, for FP32, you have 1 sum bit and 8 exponent bit and 23 fraction bit. So the sum bit like means indicates the sum of the floating point number you're going to represent, and the exponent bit can be together viewed as an integer to to denote the exponential in your floating point number, and the fraction bit can be thought as which controls the precision of the relative precision of the float point number. So here are some more examples. For FP16, there always one sum bit, but for FP16 there are like 5 exponent bit and 10 fraction bit. And BF16, which is more popular in language model pre-training or like inference, has the same number of total bits as FP16, but has a different focus. It has more exponent bit and fewer fraction bit. So the number of exponent bits in BF16 is the same as that in FP32. So that makes the transition between BF16 and FP32 more convenient. And in this work, for simplicity, we replace the positive and negative infinity value in this in the standard floating point system by just the finite numbers. So we will not encounter this not a number case and infinity case. So to actually make transformer computation on the forward path compatible with complexity theory, we have to make the parameters and input and all the intermediate computations have finite precision. Otherwise, it's like impossible to use the tools or existing results from complexity theory to capture the complexity of transformers. So it's very difficult to prove upper bound. That's like the transformers can be simulated by like finite precision circuits if it can deal with real numbers. So we have to talk about the rounding. And in this paper, the rounding we consider is so-called correct rounding. So basically, this is just the rounding that standard computers would do. Like after every binary operation, so the intermediate result is rounded to the closest representable number within this precision, within these floating point numbers. In particular, it means like you will be rounded to the closest representable number with e bits of exponents and s bits of precision. And we will denote this by this bracket with subscript es. And some more notations. So in transformers, we have like this. I think a key component we want to define here is this summation with iterative rounding. Basically, the input is a sequence of floating point numbers, and output is just a one number. And the operation is to take the sum of this sequence of numbers. And here we define this operation as the iterative version of like a binary addition. Each time you add two numbers and you round, and add a third number and you round, and that's it. And with this basic operation, we can define all these other operations we will need for transformer for the path. For example, like doing inner product. This is just doing like a Hadamard product first, and then you do this summation with iterative rounding. And with this, we can also define matrix multiplication and also finite precision softmax. Okay. So we will first present our negative result for transformers without COT. As I mentioned before, there are some existing results, but however, there's some subtlety in existing results due to the rounding, such that it do not directly apply to our case, and we have to do some new proof in our formalization of this transformers complexity. So in previous papers, it is assumed that rounding only happens after adding the entire array, which implicitly requires higher precision. So for example, if you have like log precision, so you have like both log n bits in exponents and mantissa. So if you want to do like summation without rounding and only do rounding at the final outcome, then you need to like essentially have polynomial bits to keep the like perfectly accurate intermediate results, because there are log n bits in exponents, and you need to like kind of like transform them into the fixed point numbers and then sum them up. And that transformation gives you a polynomial blow up in the precision, in the number of bits. And somehow this is crucial in the existing proof, because existing proof is based on the fact that adding n binary integers with Pauling bits belongs to TC0. Therefore, this proof also applies to the case where you have like log n bit precision and exponent floating point numbers, because you can always transfer that into Pauling-based integers with some rescaling and then summing them up and scale back. However, this does not apply to the case where you have iterative rounding. Because when you have iterative rounding, some important structure in adding integers is broken. For example, when you're adding n integers, like the position of the integers does not matter, the adding order does not matter. That I think that all makes like a parallel computation easier. But in this case, you have a specific order, and you cannot commute things very easily. And however, and also perhaps a little bit surprising, we show that in this case, the adding n numbers with O1 precision, big O1 precision, becomes even simpler if you have iterative rounding. And you can actually prove that that is within AC0. And this is kind of like the main technical improvement in, or like the difference in the negative result part for result for transformers without COT. And with this and all the remainings are the standard from the previous works, we can show that like transformers with COT, transformers without COT and Pauling embedding size is belong to AC0. And this result can be even strengthened to transformers with log n steps COT and Pauling embedding size. But this this strengthening is kind of like trivial. So you can for now just focus on the case where transformers without COT. So I will come back to this proof later. So next I will talk about our positive result. So to show the expressiveness benefit of transformers with COT, we prove the following positive result. We show that for any function Tn, if the embedding size of transformer is at least log n, then here n is the input size, then transformers with Tn steps of COT can simulate any Boolean circuits of size Tn. So that allows some like separation between transformers with and without COT. And the concrete problem that we can use as an example for separation is the so-called wording problem. Basically, you have some group, and ARG is a decision problem where a given sequence of group elements is asking whether a given sequence of group elements has a product equal to identity. And in particular, we can choose S5 to be the symmetric group of, we can choose S5 to be the G here, and S5 is a symmetric group over 5 elements. And there's a classic result from Barrington in 1986, saying that the wording group of S5 is NC1 complete. And this completeness is under AC0 reductions. Therefore, we have the following results. So basically, it's quite like easy to show that LS5 can be solved by like linear size circuits, because this is just like doing group composition n times. And by theorem 3, we know the wording problem of S5 also belongs to the like transformers with n steps of COT and log n embedding size. And if we further assume there's a separation between TC0 and NC1, then that means there is some problem that is in NC1 but not in TC0. Then we can have like AC0 reduction from that problem to LS5. And that means LS5 is also not in TC0. And we have just talked about that transformers without chain of thought is a subset of AC0, and that implies this wording problem of LS5 cannot be solved by transformers without chain of thought, even if you have like poly embedding size. Okay, so that's like the main positive result in the paper. Any questions? So next, I will talk about the proof sketch of this positive result, which is quite straightforward. Indeed, we can even like use a single layer transformer with two attention heads to simulate this, to simulate any Tn size Boolean circuit. And the high level idea is to simulate any non-input gate of Boolean circuit with steps of COT. And in particular, we can use one step of COT to simulate one non-input gate in this target Boolean circuit. So the way to construct this transformer given a circuit is to first serialize the circuit along the topological order of the gates into some format, which is some like standard, maybe called direct connection form in some literature. And then we can store this information of the circuit into the absolute position encoding at position I. And here we need, the reason that we need log n embedding size is because they are totally n gates or like poly n gates. If you consider the length of COT, and you need like a bigger log n dimensions of like +1, -1 to store those different gate numbers. And then we can use attention to hook the gate values of the two input gate of current gate, which is computed from the past, and then use MLP to simulate the current gate. So this is a little bit abstract, and I will demonstrate the construction in a concrete example. So this is a concrete two non-input gate circuit. And this is how we serialize this circuit. So there are 4 gates. And in each row, we have gate ID and the gate type and the ID of the IDs of the two input gate of the current gate. So this is this information is stored in this blue table. And to construct transformer, I will first shift the blue table and get the green table. So green table has like one less row than the blue table. This is because at each row of the green table, say at gate ID 2, I store the information about the next gate, because at gate ID 2, I want to, after forward pass, I want to generate the token stored at position 3, or the gate value of the gate 3. So I can write that back to a tape. That's why at gate 2, I will get information. I will need to have information about gate 3. And once we have the green table, we can use like just one layer transformer to do this computation. So here the information of this circuit for each gate is stored in the position embedding. And here the position embedding for the third gate includes like 3 and 2 and 3. So for the last 2 and 3, the last two digits, they are in different colors. And in the attention layer, you can see they are used as queries to attend they are used as queries to attend past keys. Such that it can the current gate, the forward pass at current token can use that to hook the computed gate value from the path gate x2 and x3, and that will be fitted into MLP layer. And the gate type AND, which is stored in the position embedding, will also be directly fed into MLP layer. And the MLP layer will just compute the output of this AND gate with the input being x2 and x3, and that is x4, and will be written back to the tape. So this proof is based on induction, and at this step, I'm assuming all the previous tokens, all the forward paths of previous token positions are already like done as I said, and the correct value of the next gate has been computed and feed back to the tape. So any question here? So that basically completes the proof. It's really very simple. And throughout the whole process, you just need like constant precision because there's like no fancy operations in attention to do summation. Attention is basically just used as just a hard attention to extract the value from the using keys from the past positions. So next, I want to show some empirical verifications of the theory. So basically, we consider four synthetic tasks, including modular addition and the composition of S5, and iterative squaring and circular value problems. So we could consider three settings, which are base, and hint, and COT. So for the base setting, we train on the answer of the problem f star x directly. Here, x is the input sequence. And for COT, we have a manually designed chain of thought, which is denoted by dx. And in this case, we happen to be able to make the COT have the same length, which is linear length, in terms of n. And the last bit of COT is the answer. However, even if we empirically find COT is better, it could be that the manually designed COT provides just more information, which makes the learning problem statistically easier. So we design another setting, another controlled experiment called hint. So in this case, we give the language model the same amount of information we give to language model in a COT setting. However, we do not increase the computational power of the model. In detail, we use COT as a supervision for transformer outputs at input positions. So this does not always make sense, but somehow in these four selected synthetic tasks, it somehow makes sense. And we are training from scratch and using Adam, and we do 1 million steps of training, and each step takes like 64 fresh samples. So this is the result. So this is for modular addition where p is equal to 7. So here I only presented the result for hint and COT and omitted for base. That is because in the case of like a base setting, the optimization is too difficult. Even though in terms maybe expressiveness, it is same as hint. But due to the optimization issue, the performance in base is always dominated by the performance in hint. And here what we really care is about the transformer's expressiveness of the transformer instead of the optimization of the transformer. So we only present hint. So as we can see from the figures, we have DOT. No matter how deep the transformer is, uh, sorry, no matter how long the input sequence is, um, as long as you have COT, you can get like 100% training accuracy. But for transformers without COT, which is this hinge setting, even if it has all the intermediate supervisions, but when length becomes larger, you need actually to make the transformer deeper to increase the performance. So next experiment is about S5. Um, so here the supervision, the COT is like one token shorter than the input token, but so there's like slight discrepancy between this exact setting here and the general setting I discussed in the discussed 2 slides ago, but I think this is a minor issue. We can just ignore that. The high level message is still the same here. If you have COT, as long as your length becomes your depth becomes larger than 2, you can get like 100% training accuracy on all lenses. But if you don't have COT, you actually need to use a larger depth to get higher or like 100% training accuracy on longer input sequences. Here, because I'm talking about S5, and the way I measure accuracy is uh, I count how many numbers in the final permutation is correct. So that means if you just random guess the permutation, the accuracy will be 20%. And that's what you're seeing in the figure on the right, figure on the left. So 20% means like random guessing. So here B is the input string, like basically you have 3 permutations, and A is their like partial computation, and the last permutation in A is the answer. And A is the string A is a COT, and if you put string A after string B, it makes it a standard COT setting. And if you just use string A as a supervision for string B, and keeps the input length as long as the string B, then it becomes the hinted setting, where you don't increase the computational power of transformer, but you keep some extra supervision in the training. So any questions here? So the next task is iterative squaring. So basically, the input format is first you have some P and then some number R, and you have like a sequence of like square operations. And the task is to output the outcome of R after being squared like say n times and mod P. So this is used as some hardness assumption in some cryptography literature. Here we're not doing the exact task, which makes it like that hard in cryptography that can be used as a hardness assumption. But we're using some like simplified, modified version, but it seems to be hard enough for transformers without COT. But again, with COT, it can get perfect training accuracy. And the last example is circuit value problem. The task here is given a serialized description of the circuits and ask the transformer to output the final output or the output of the last gate of the circuit. So this problem is known to be P-complete. So therefore we can kind of like believe that this problem cannot be solved by transformers with constant depth and without COT. And experiments also support that. So these are all the experiments I have. And the conclusion from this empirical studies is that indeed the COT allows transformer to compute incrementally serial problems. Okay, so that's for experiments. Next, I will talk about the proof for negative result for transformer without COT, that this transformer without COT, even with Pauling embedding size, is actually a subset of AC0. instead of just TC0. So the high-level idea here is to show that summation with iterative rounding is in AC0 if your precision is constant. Because all the remaining operations, they're essentially binary operations for finite bit numbers, and they can, of course, be simulated by AC0 circuits. And here, as a recap, this is summation with iterative rounding. And the way to prove it is in AC0, or it can be simulated by some AC0 circuits, is to view this summation with iterative rounding as an automaton. Here, the alphabet, sigma, and the states q both equal to the set of representable numbers with e bits of exponents and s bits of significance. And we denote this by FES. And the transition function is defined by the following function delta. We are taking state q and symbol sigma, which are both like the numbers from FES, and just output the result of correct rounding of q plus sigma. So this is straightforward. And we can also do a standard extension of this automaton transition function to words instead of just a single symbol in the alphabet. And the definition just, if you have a word, then the transition function given the word is just to apply a sequence of transitions for each token in this word. Okay, so the key result or the key lemma that we are going to use to prove that this automaton can be simulated by AC0 circuit is that is the following Krohn-Royce decomposition theorem. This is not the full theorem. It is just like a particular case of the theorem. And in this case, it reads as like if the automaton is counter-free, then it can be simulated by some AC0 circuits. There are a few different characterizations, different and equivalent characterizations of counter-free language. So counter-free automaton. Like for example, if this language is star-free, basically regular language without cleaning star, or the transformation semi-group of the automaton is aperiodic. And in this case, we will use the later definition to complete the proof. In detail, we are going to prove that the transformation semi-group of this automaton is aperiodic. So here, the important property that we are going to use about this automaton is that this transition delta always preserves the order of the state as real numbers. In other words, if you have any two states q and q prime, and say q is larger than q prime, then what we know is that no matter like what sigma you have from this FES, after this single step transition, the new state for q is always larger than, at least not smaller than the new state get from q prime. This is true because of the definition of the correct rounding. And we show that all such ordered automaton, which can be equipped with the order and the transition preserves the order, is counter-free. And proof is actually very simple. So taking any word and state q, and without lots of generality, we can do the delta qw is larger than q. And because it preserves order, if we further apply this transition delta w, we know this sequence will be monotone non-decreasing. But the alphabet is also, the state space is finite. So starting from some kq, depending on the q, which is smaller than the size of the alphabet and the state space, this sequence has to be exact strict equality. And therefore, it suffices to take K to be the size of state space. And this will ensure that delta QWK is equal to delta QWK plus 1 for every W and every Q. So this is exactly the definition of the aperiodic transformation semigroup. And that means this automaton can be simulated by some AC0 circuits. So any questions here? Okay. So next we want to discuss about some extension results of our result to polynomial embedding size. So this actually gives rise to an interesting new complexity class. So the result here is that if we have polynomial embedding size and you have Tn steps of COT, you can actually simulate, or the complexity class of COT is exactly equal to the following defined Tn size circuits, but equipped with some single output AC0 oracle gates. In other words, this size AC0 Tn refers to the circuits where you have Tn gates, where each gate in this circuit is an AC0 oracle gate. It can be an AC0 subcircuit with only one single output, but it can have like polynomially many inputs. So in some sense, this is saying that like if you have poly n embedding size and Tn steps of COT, you can do very powerful computations, but somehow you have some restriction on the amount of information that you can store as intermediate values. And here in the case of transformers means that you have some restriction on the amount of information you can read back to tapes. It's quite interesting for me to understand the difference between this function class versus standard like a transformer, but just with like a Tn times larger depths. But somehow I don't have like a lot of interesting things to say about that. I'm still thinking about that problem. But one interesting implication for this theorem is that it means that for constant depth transformers, if you have poly n embedding size, then log n steps of COT is not more powerful than just to have poly n embedding size without COT. Basically, if you have poly n embedding size, log n steps COT is useless in terms of expressiveness. So this is because for like size n AC0 log n, where you have like a log n intermediate output for the oracle AC0 gates, you can simulate them just by some single AC0 circuit, which with potentially more to the number of gates, but it's still AC0. And the way to do that is to just guess and verify these all log n intermediate outputs in parallel. So you can have like polynomially many parallel guess process, and for each subprocess, you specify values for these log n gates, and you verify if this is possible. And this can be done in constant depths. So therefore, it's exactly the same expressiveness as just AC0 if you have like log n Tn equal to log n. And this further completes the negative results because it says that like COT with log n transformers with log n steps of COT and poly embedding size is still in AC0. And this is a summarization of the results. So the horizontal axis is for the length of COT, and the vertical axis is for the embedding size of the model, where n is the input sequence length. And in red font, we give some existing equivalent class in complexity theory for our newly defined COT family. So basically, we show that is for every polynomial Tn, there is an NC1 complete problem. The constant depth decoder only transformer with log n embedding size can solve with Tn steps of COT. But it cannot solve with only log n steps of COT. And this is because we take the hardness assumption that NC1 is not equal to T0, and that's AC0. and therefore any NC1 complete problems on the AC0 reductions are not in AC0, and not to mention log n steps of COT. And on the other hand, transformers with Tn steps of COT can simulate size Tn circuits, and size Tn circuits always contain some NC1 complete problem. And here the take-home message is exactly the title of the paper. Like COT can empower the transformer to compute inherently serial problems. Okay, so in the last few minutes, I want to discuss about the approach in this paper compared to some related works. So there's some concurrent work by Maria and Zaparo showing that like a fixed transformer with log n precision and saturated attention can simulate Turing machine, which is another way to show that with COT you can go beyond these T0, AC0 limits. Like their construction or their proof essentially simplifies it kind of like has the same idea of the, sorry, there's a typo, has the same idea as a press AO in like 2021, but they simplify the assumption. The price error is not published in actual 24. It's actually, I think, in JMR 21. And the same idea here is that they use the one step of COT to simulate one step of Turing machine transition, which means you need to write down left or right and the current state and the current symbol. And to simulate Turing machine, and one need to use attention layer to do two things. And the first thing is to do summation over the past moving directions. And second thing is just looking up, which is you always need to do. However, the one potential issue here is that the summation over the past moving directions actually requires like a much higher precision than constant precision. It could be challenging in some popular practical settings. So for example, as I said before, like BF16 has like 7 digits for mantissa. And that means you cannot represent any number between 256 and 258 in BF16. That means you can basically not get the position 257 in BF16. But some popular like foundation models have much larger input length than 256. For example, Llama 2 supports like 4,000 and Llama 3.1 supports like 128,000. So that would make like the Turing machine construction a little bit difficult to extract the exact position at this magnitude of like length if you are going to use BF16. But however, BF16 is kind of like the default for all these like large language models. So in comparison, our construction has the benefit that it only uses constant precision, but at the cost, we need to make the embedding size grow with sequence length, which is at the magnitude of like at the order of log n. So that's kind of like one of the benefits of our construction, but we also have some caveats. And the main caveat is that our positive result like heavily relies on the usage of absolute position embedding. And this construction does not work for like more popular rotary position embedding. And also unlike Turing machine, the circuit is a non-uniform computational model, and we do not provide a construction which works for all input lengths. And instead we just provide a construction for like circuits that is up to some input length. And for the same reason, it's quite clear that the current construction cannot generalize across lengths or generalize to unseen longer lengths. This is because transformer cannot learn like unseen positional embeddings. And of course, there are like multiple difficulty to get length generalization, and this is not the only one. But at least I would say this is the biggest issue or the most direct issue for the current construction. There are also some issue about practical relevance. Like in this paper, we assume the vocabulary size and the depth of transformer is constant, and we had their dependency in the final bound. However, it's not quite clear what is the right regime in practice, or what is the most practically interesting regime. For example, Llama 3.1 has like a 405 billion parameters with a context length of 128K. And its vocabulary size is also 128K, which is as large as N. And also, the fully connected network has the embedding size of like 53,000, which is also almost as large as N. And depth is 128, which is much larger than log N. So probably the lower bound in this paper does not really directly apply to this like foundation models, like large foundation models in practice. But I feel like still, like when you're enabling COT, you can see some benefit in reasoning ability. And also there are some recent results by Zhiyuan, Zhu, and Yuanzhi Li on like physics in large language models. They also confirm that for reasoning tasks, scaling in depth is also more useful than scaling in width, which is unlike these knowledge extraction cases. So that still makes me feel like the depth is crucial, the condition depth is crucial in reasoning tasks, but we probably need some more fine-grained characterization to make these results practically relevant and provide like a good guidance in practice. Okay, so finally I want to talk about some future directions. So the first thing is some more discussion on non-uniformity. So this is a short summarization of the different kind of like non-uniform or uniformity you can have. So in this paper, we present a construction which is basically at the bottom level, like you have different model for each input length in Fn steps COT, where this F is some function of n. And we could make our construction slightly better than into the following case. You can have a single model which solves all the input lengths up to some n max and using Fn max steps. And this is kind of like trivial, but you can just do this by pad the short input length to n max input length and use the same circuit to solve all these problems. And something even better would be use a single model to solve all these lengths up to some n max, and the number of COTs is proportional to the input length. That means for simpler models, simpler problems, we want to use less computational resource. And in the ideal case, we want to remove this even restriction of like n max. This is like a Turing machine or uniform computing model, and this is something it's clear that cannot be done by the construction in this paper. But somehow I feel like it's possible to extend the construction in this paper to the third level, where you can have like fewer COT steps. You can have a single model up to some maximum length, which could be very large, and the number of COT steps depends on the input length. That's probably possible. So there's some other general future directions, like for example, how to design position encodings, which allows better length generation. This will be twofold. On one hand, we want the position encoding to be powerful enough to express these computable functions. On the other hand, we want it don't be too powerful. So this OOD generation across lengths won't be too difficult. And the other question is like, how does this zero-shot COT ability emerge from pre-training, even if you don't have exact training data that looks like the test data set? And third question is like, how to learn COT when there is no explicit supervision in pre-training. So like, even though we show that like a COT can simulate any size T in circuits, which seems to be very powerful, but this is not very useful in the sense that we can only construct such COT for problems we already know how to solve. But the purpose of machine learning is just to use like a data and label to do this like a kind of like a end-to-end learning without like human efforts. But here we can only use COT to design problems, to solve problems that we know how to solve, and how to design how to design a manual COT that can be understood by transformers, which is not quite satisfying. And the more interesting problem would be to allow COT in the architecture and less transformer to figure out what could be a reasonable COT by itself. But that sounds like needs some like reinforcement learning, and it's quite non-trivial. And yeah, I don't have any good idea about that. So yeah, that's all I have for this talk. Thank you.